Suppose that C1, C2, C3 is a sequence defined as follows. C sub 0 equals 1, C sub 1 equals 1, C sub k equals C sub the floor of k over 2, plus C sub the ceiling of k over 2 for every integer k greater than or equal to 2. Prove that C sub n equals n for each integer n greater than or equal to 1. Now, just a reminder, the floor function just takes a real number and rounds down. So it finds the greatest integer that is less than whatever the number is. So, for example, the floor of 5.3 is just 5. The floor of 9.718 is just 9. The floor of pi is 3. The ceiling function rounds a number up. So whatever the number is, if there's a decimal, then the number is rounded up to the next consecutive integer. So the ceiling of pi would be 4. The ceiling of 9.1 would be 10. So we're going to prove this with strong mathematical induction. First, we're going to identify the predicate P of n, which is the thing that we're proving minus the universal quantifier portion. So this part here is our P of n. Now, if you notice, they gave us two initial conditions. Usually, and this is not always the case, usually the number of initial values that they give you in the sequence is also the number of base cases that you'll need. In this case, we will need two base cases. But you'll see why we'll need two base cases more so when we get to the inductive step, where we'll need to split up our inductive step into two different cases. And those cases will be handled differently based upon this recurrence relation. But we'll get to all that once we get to the inductive step. Now, I've mentioned in a previous video that the number of base cases is the difference between the largest index and the smallest index. This is going to be the first problem that we do where that is not the case, where the difference between these two numbers isn't the number of base cases. Actually, we're going to get away with only doing two base cases. But it's because of the trick that we use in the inductive step that will justify why we need to only use two base cases here. Now we have to prove that P of n is true for all n greater than or equal to 1. So that means our first base case is going to correspond to when n equals 1, which is the smallest integer, such that P of n is true. But we need to prove two base cases. So we're going to show that this is true for n equals 1, and we're going to show that this is true for n equals 2 as well. Let's start with P of 1. P of 1 is the claim that C sub 1 equals 1. Now, I'm going to put a question mark here because I don't want to just assert the conclusion. However, this conclusion is easily assertable since we're literally given that C sub 1 equals 1. Now, notice how P of 1 requires us to know information about C sub 1 and not C sub 0. Now let's move on to P of 2. P of 2 is the claim that C sub 2 equals 2. Now I'm going to put a question mark here. This one is not so easy to conclude because we actually have to prove this. We're not just given this information. Why is C sub 2 equal to 2? Why would that be? Well, what we can do is we can use our recurrence relation here, which can apply for every integer greater than or equal to 2. So that means I can plug in k equals 2 into this recurrence relation to get C sub 2 equals C sub the floor of 2 over 2 plus C sub the ceiling of 2 over 2. Now 2 divided by 2 is just 1. And if you round 1 down, you just get 1. And if you round 1 up, you also get 1. So this says that C sub 2 equals C sub 1 plus C sub 1. And we already know what C sub 1 is. C sub 1 is 1. This is given to us. So this is 1 plus 1, which equals 2. And that's what we wanted to prove. We wanted to prove that P of 2 is true, that C sub 2 actually does equal 2. So we've proven that P of n is true for n equals 1 and n equals 2. Let's move on to the inductive step. Now we start all inductive steps the same with let k be an arbitrary fixed integer. And now we're going to make specifications to k, and we're going to make assumptions about P of n for certain values of n. Now in strong mathematical induction, we want to assume that k is greater than or equal to the largest base case, which in this case means that k is greater than or equal to 2. And then we're going to assume that for all 1, the smallest base case here, less than or equal to I, less than or equal to k, P of I is true. So altogether, let k be an arbitrary fixed integer such that k is greater than or equal to 2, and assume that for all 1 less than or equal to I less than or equal to k, P of I is true. So we're assuming that P of 1 is true. We're assuming that P of 2 is true, and so on, all the way up to P of k. We're assuming that all of those are true. We need to show that P of k plus 1 is true. So what does it mean that P of I is true for all of these values? Well, that means that C sub 1 equals 1. That's P of 1. We know this to be true. C sub 2 equals 2. That's P of 2. And this goes all the way to C sub k equals k. We get to assume that all of these are true. What we really need to ask is C sub k plus 1 equal to k plus 1? And why? Now the proof here is going to be pretty tricky. Now the trick to this proof is to break it up into cases. Either k plus 1 is going to be even or k plus 1 is going to be odd. This is going to be really important when we apply the recursive definition of the sequence. Let's start with the case where k plus 1 is even. If that's the case, then this means that k plus 1 equals 2l for some integer l. That's the definition of an even number. And remember that by assumption, k is greater than or equal to 2, which means that k plus 1 is greater than or equal to 2 as well. It's actually greater than or equal to 3, but we need to justify that it's greater than or equal to 2 in order to apply the recursive definition of the sequence. This recursive definition only applies for integers that are greater than or equal to 2, but luckily k plus 1 is greater than or equal to 2. So I'm going to apply this recursive definition to k plus 1, which is going to require a shift in the index. I'm going to replace all of these k's with k plus 1 instead, since it applies for every integer that's greater than or equal to 2, including k plus 1. So this means then that c sub k plus 1 equals c sub the floor of k plus 1 over 2 plus c sub the ceiling of k plus 1 over 2. Now, we know that k plus 1 is even, so I'm going to substitute 2l into k plus 1 here. So this is equal to c sub the floor of 2l over 2 plus c sub the ceiling of 2l over 2. The 2's cancel, so this equals c sub the floor of l plus c sub the ceiling of l. But keep in mind, l is, by the definition of an even integer, l is an integer, which means that if you take the floor of an integer or the ceiling of an integer, you just get that integer. So this is c sub l plus c sub l. Now here's where things get interesting. L satisfies this inequality. L is one of these i's that is sandwiched between the numbers 1 and k. Let's talk about why that would be. Now, since k plus 1 is a positive integer, that means L is a positive integer. But k plus 1 is twice the size of L. Now that means that L is strictly less than k plus 1, but it's also greater than or equal to 1 because we know L has to be positive since k plus 1 is positive. But more importantly, this means that L satisfies the inequality that it's sandwiched between 1 and k. And that means precisely that P of L is true. Now, this is the part where we are applying the inductive hypothesis. So let's remind ourselves what our inductive hypothesis is. Our inductive hypothesis says that P of L is true, P of L, since L is one of the i's that satisfy this inequality. And so that means somewhere in this list of P of i's, somewhere in here is the statement that C sub L equals L. We don't know what L is, but we know that it's somewhere buried in those dots here. That's because L satisfies this inequality. So what does this mean? That means that we can rewrite this C sub L plus C sub L as just L plus L, since C sub L equals L by the inductive hypothesis. And this is equal to 2L. Now we know from earlier that 2L equals K plus 1. So this equals K plus 1. So what have we shown? We've just shown that C sub K plus 1 here is equal to this, which is equal to that, which is equal to that, which is equal to that, which is equal to this, which is equal to 2L, which equals K plus 1. And so C sub K plus 1 equals K plus 1. That's what we wanted to show. That's for case 1. Now we have to get to case 2, which is going to be more or less the same proof, same structure. Now, by definition of an odd integer, this means that K plus 1 equals 2L plus 1. Keep in mind that this L is a temporary variable, and the scope of it only extends to this case. So the L in case 1 has nothing to do with this L in case 2. The scopes of those don't overlap in any way. And this is true for some integer L. Now, what do we do after this in case 1? The next thing we did is we justified why we can use the recursive definition. So since K is greater than or equal to 2, this means then that K plus 1 is greater than or equal to 3. And in particular, it's actually greater than or equal to 2 as well, since 3 is bigger than 2. But it's important to emphasize that it's greater than or equal to 2 so that we can apply the recursive definition to C sub K plus 1. This is equal to C sub the floor of K plus 1 over 2 plus C sub the ceiling of K plus 1 over 2. So just like we did in case 1, we're going to substitute 2L plus 1 into the numerators of these fractions here. So this is equal to C sub the floor of 2L plus 1 over 2 plus C sub the ceiling of 2L plus 1 over 2. Now we can rewrite this as C sub the floor of L plus 1/2 plus C sub the ceiling of L plus 1/2. L is an integer. So let's think about what happens when we round down or round up these numbers here. This L plus 1/2. Since L is an integer, then L plus 1/2 will round down back down to L. So this is the same thing as C sub L. C sub the ceiling of L plus 1/2, since L is an integer, L plus 1/2 is going to round up to the next integer, which in this case will be C sub L plus 1. Now this is where we justify why we did 2 base cases. Notice here, in this case, we need to prove that C sub L and C sub L plus 1 both satisfy the inequality that needs to be satisfied in order to apply the inductive hypothesis here. Now, since K plus 1 is greater than or equal to 3, then this means that L has to be greater than or equal to 1. But this also means that L plus 1 is also greater than or equal to 1. That's the first half of the inequality that needs to be satisfied in order for us to apply the inductive hypothesis. The next thing we need to show is that L and L plus 1 are less than or equal to K. Now we can use the fact that K plus 1 equals 2L plus 1 and subtract 1 on both sides to get K equals 2L. Now this means L is strictly less than K, which is the same way as saying that L is less than or equal to K minus 1. But if we add 1 to both sides of this equation, this also means that L plus 1 is less than or equal to K. Whereas this inequality tells us that L is less than or equal to K. And now we have all the pieces to the puzzle. We've shown that L is less than or equal to K and L is greater than or equal to 1. So that means that 1 is less than or equal to L, which is less than or equal to K. And we've shown that L plus 1 is less than or equal to K, and L plus 1 is greater than or equal to 1. So that means 1 is less than or equal to L plus 1, which is less than or equal to K. This is all extremely important. This inequality has to be satisfied specifically like this in order for us to properly apply the inductive hypothesis. So this is where we get to say that P of L and P of L plus 1 are both true, which means that C sub L equals L and C sub L plus 1 equals L plus 1. Since this is where we are applying the inductive hypothesis, we need to clarify that this is by the inductive hypothesis. Okay, so what do we get then? So now we can take this expression here, C sub L plus C sub L plus 1, and we could say this is the same thing as L plus L plus 1, using substitution here. But this is just 2L plus 1, and 2L plus 1 is equal to K plus 1. And so we have concluded that C sub K plus 1 is equal to K plus 1. In other words, in either case, C sub K plus 1 equals K plus 1. And this means that P of K plus 1 is true. And now we can conclude that by strong mathematical induction, P of n is true for all n greater than or equal to 1. Now, I really want to emphasize the trickiest part of this proof is getting these inequalities correctly here, and also knowing to use two base cases, since L and L plus 1 are two different integers. And so we're applying the inductive hypothesis to two different P of i's. There's P of L and P of L plus 1. But we don't get two free P of i's unless K is greater than or equal to 2. And so if I starts at 1 and goes up to K, then that means we're assuming at least two P of i's, P of 1 and P of 2. We are assuming at least those are both true, which requires us to justify P of 1 and P of 2. I will say, though, for case 1, there is no reason why we needed two base cases for this part, because we only had C sub L and C sub L, and L is just one integer. And so we only needed to apply the inductive hypothesis to one case specifically, one P of I. Anyways, thanks everyone, and I'll see you in the next video.